Thank you, Gary. Thank you, everyone, for giving me this platform to talk to you. I hope you can have a nice start of the Friday afternoon, just leading to the weekend. So today, our aim is to have a look at what neutron scattering can do, and specifically neutron spectroscopy, because we had already two talks by neutron experts. And they were covering what you can do with, in particular, small angle scattering with Sarah Rogers, and Ralph Gillis talked about battery applications. So I wanted to focus today on an overview what you can do with neutron spectroscopy. And I will have some quite specific examples that also show how you can link the neutron spectroscopy with the knowledge you gain from other techniques. So just to give a short content overview, I will first talk about a little bit why we want to use neutrons, how they are produced specifically at ILL, a reactor source. Then a little bit about different spectroscopy techniques, and without going into too much detail. And then I will try to cover in my time a few scientific examples to give you an overview of what you can do and how it's done. So the neutron sources that we have in REMATE, there are 5 of them. They are all members of the network LENS. We have in the UK ISIS as a spallation source. We have PSI in Switzerland, who have a synchrotron and neutron source, most notably. We have the Hans Meyer-Leibniz Zentrum with a reactor in Garching next to Munich. And in Budapest, we have the Hungarian neutron source BNC. And last but not least, ILL, the Institut Laue-Langevin, based on the same campus as Gary's institute, the ESRF. So we have also, like at PSI and like on the ISIS campus, a synchrotron and a neutron source on the same site. Why do you use neutrons? Already Sarah touched that a little bit. Just as a reminder here, the neutrons are electrically neutral, so they can penetrate deep into matter. They have a spin, a nuclear spin. So with that, you can also look at magnetic diffraction, for example. In the energy range with which we use neutrons, you can get an angstrom range wavelength, which means that in terms of scattering properties, in terms of diffraction, you can get a spatial resolution of the angstrom range as well, which is important to look at matter on an atomic length scale. And finally, you have very low kinetic energy. So for us, it's pretty easy to get milli-electron volt energy resolution, or even down to micro or nano electron volt in some extreme applications. And what's very interesting, that makes the neutrons very complementary to X-rays. That's shown here on the right-hand side graph. When you look at this, at the scattering cross sections of X-rays on the left and neutrons on the right, you see that X-rays, the scattering cross section is guided by the number of electrons in the material, in the atoms. Whereas for neutrons, we have a nuclear interaction, and by quantum mechanical effects, the neutrons have the highest scattering cross-section for hydrogen, which makes this hydrogen very, very visible for us. And you can play also using quantum mechanics, some other tricks. You have actually a negative so-called scattering length for hydrogen. And this means that if you have the right mixture of hydrogen and deuterium, which is the variant of hydrogen with 1 neutron more, then you can get reduce contrast, or you can pronounce certain parts of a sample, of a hydrogenous sample, and change contrast in your sample and make some parts of, for example, polymer assemblies visible and others disappear. It's used in this research, for example, with small angle scattering that Sarah showed. Now, we produce the neutrons with a reactor at ILL. And what you can see here is a cut through the reactor building. And in the middle, we have the center of the reactor. That's where we create our neutrons with a nuclear reaction. And they are extracted around the core of the reactor with neutron guides and brought to the instruments. Now I have a little animation of first how the neutrons are created. So whenever you have a fission process, we create 2.5 fast neutrons. And these neutrons, they can partly be extracted, and part of them are used to maintain the nuclear reaction. And with this process, we can get at ILL a very, very high flux of neutrons that we can use as light source. But you have to think of our neutrons as kind of this very specific kind of light, just like the X-rays you have in a synchrotron source. Now, when you look at this assembly here, we have several fingers showing next to the reactor. And what we do there is we have several containers of cold liquids next to the reactor, just to tune the distribution of energies of the neutrons. The colder the source that we have, it's just like a light source. The colder the source, the colder the light. And I show you in a little film here how this is done. So the neutrons come out of the reactor. They go into the guides after they have been in the energy moderator. Then they come to an energy selecting monochromator, then the sample, then an analyzer, and then they are detected, artistically shown here. And with that, you can get information about how these samples move in our case. You can either look at the positions or how they move. And what we are with spectroscopy concerned with is the motion of the atoms in the samples. Now, the whole setup at ILL is shown here. We have on the bottom left corner the reactor building. There are quite a few instruments already in the building of the reactor. And then there are neutron guides, which are mirror assemblies, basically, which guide the neutrons out to instruments that can be up to about 100 meters away from the reactor core. And they are all in 2 large guide holes. And that's where you would find the instruments when you do experiments at ILL. Now, the spectroscopic window that we can cover, that's shown here. I extracted that from a relatively recent publication. And you see here in this graph, maybe you can look at that later more in detail when we have the YouTube video of this seminar online. Just to draw your attention to the center, we have different types of spectroscopy, all these colored blobs here that are different neutron spectroscopy techniques, time of flight spectroscopy, backscattering spectroscopy, spin-echo spectroscopy, and they can cover huge ranges. Oh, I wanted to go back here. Huge ranges of length scales. So you see these length scale displayed on the bottom line here. So that goes from the micrometer to the nanometer, to the from the micrometer upwards, from nanometer upwards. And then you have the time scales that are between microsecond and picosecond and below. And this can all be covered at the same time. And the nice thing about neutron scattering is that you get the spatial information and the spectroscopic information, the time information in the same time. And just for comparison, you see quite a few different other spectroscopic techniques in comparison to what we do. You have infrared spectroscopy, Raman spectroscopy, dynamic light scattering, X-ray spectroscopy techniques. So it's a wide range of different types of motion that you can cover with this. And here we will just cover a few examples. Now, in a generalized way, what you do in a neutron scattering experiment or any spectroscopy experiments, you come in with a pretty white light. You apply energy filter, do scattering from the sample. Then you apply further energy filter and you measure the signal in the detector. And the information that you extract, normally categorize it by splitting it up into what's happening in different momentum transfers and different energy transfers. And you do that because splitting this up in this way gives you a lot of information that lets you compare the data to, for example, molecular dynamic simulations. Now, the first spectroscopy that I want to just highlight that we have, for example, at ILL, that's the vibrational spectroscopy. That's on the fast neutron end. And one very useful spectrometer that we have for looking at hydrogen-containing materials, for example, is Lagrange. Lagrange is a very recent and very, very high flux instrument where you can use, in neutron standards, very small samples. You come in with a beam from a monochromator that comes directly from our hot source, illuminate the sample, and then you have a large shield of, well, you can see it better in the 3D view around here, that large shield of monochromator crystals. So they select an energy, but they are built all around here. And then you illuminate with this detector at the bottom of the instrument. And this gives you a very large signal. And then scanning through energies, you can record a spectrum. And here's an example of hydrogen in a C60, in C60 buckyballs. And you see the very lines that you can detect. And this spectroscopy, of course, covers the similar spectral range as, for example, Raman and infrared spectroscopy. But you can investigate with this samples which are not available for, not attackable with Raman or infrared, for example, because they are black and not transparent to light. Now, the second spectroscopy technique that we use very much here at the Neutron facilities, that's the time-of-flight spectroscopy. That's the spectroscopy. Well, here I show you a spectrometer ion 5. In that spectroscopy, you have a white beam of cold neutrons that come from a liquid hydrogen source from the close to the reactor, and then this beam is chopped into little pulses with so-called chopper disks, which are blades with holes in them. And they cut this neutron beam into pulses that fly through the instrument, hit the sample, and then you have a detection of the signal at the detectors all around. And you can see it here in a 3D print. And as a function of time, you see when the neutrons arrive at the detector. And arrival time that can be recalculated into energy transfer, because time is related to a speed of the neutrons, and speed is related to the kinetic energy. And that lets us deduce afterwards if we have, for example, excitations, or if we have other diffusive energy transfers at the sample. Now, a last technique that's very specific for neutrons, and that's the spectrometer where I work at, the spectrometer WASP at ILL. There we do a very high resolution technique by exploiting the neutron spin. And we expose this spin to a magnetic field. And with this magnetic field, we split up the wave function of the neutron in two parts. These two parts will interact with the sample with a time difference t, and then recombined in the second half of the spectrometer with an opposite magnetic field. And then at the end of this spectrometer, you can measure the loss of polarization of the spin property. And this loss of coherence, that shows you if what the structural correlation function does at the sample with time. So this neutron spin echo spectroscopy measures the decay of the structural correlation function with time. So that's the high resolution, one of the high resolution techniques. And now I want to go to scientific examples. And I start with a very specific example where I'm involved in myself as a thesis supervisor. And that's a project that we do with a university in Germany, with Westfälische Hochschule. And there we look at the mobility of hydrogen and the reactivity of hydrogen in some catalysts that are alternative to platinum. Why do we do this? We do this because well, hydrogen is a very important energy carrier if you want to look into a more circular economy in the future, where we want to get away from fossil fuels and to reach larger ranges, and especially in heavyweight transporters on road, lorries, or on sea. Hydrogen is a very good energy carrier that scales very well if you upscale the load when it gets very complicated for batteries to operate. But for the production of green hydrogen, we have a big bottleneck at some point, because there's a catalyst that you need for this when you want to break up water into hydrogen and oxygen. And at the moment, this is largely done with platinum and iridium as catalysts. And they are, first of all, extremely expensive compared to other materials. And they have to be extracted from the ground, and they are effectively very rare. So if you upscale the production to what would be needed in the future, it's hardly invisible to cover this all with platinum and iridium. So we need to have alternative catalysts. That's what we are working on. So this molybdenum sulfide that we are working on is a layered material, and it's highly porous. And of course, there have been studies on the structure, but about the mobility of the hydrogen in this material, it's very little is known. And what I find interesting in this case as an example is that here we already, before remade started, we saw the need to cover quite a few different techniques that are a part of remade, most notably, of course, neutron powder diffraction and spectroscopy, but also different X-ray techniques, diffraction, spectroscopy, XPS and NEXAS, but also beams, nuclear reaction analysis, and infrared and Raman spectroscopy. Now, for looking at this, we had to, if you look at these samples and want to study hydrogen motion, you're often confronted with the fact that there's also water inside, of course, because you have basically the whole process happens in water. So you have to look at differentiating the motion of the different hydrogens in your sample. So what we did is, first of all, we looked at very specific samples. We looked at molybdenum sulfide single crystals. You can see them here just as a general image, and here you see them put in a sample holder. It's a flat aluminum cell of about, the inner part is about 2 by 3 centimeters. And we looked at different kinds of sample preparations. Once we soaked them just in water without any chemistry attached. We atom bombarded the single crystals, and we loaded them via electrolysis. Now, then we exposed them to the different techniques that are at our hands. So for the soaked crystals, so just soaked in demineralized water, when we looked at them with the nuclear reaction analysis, where you expose the samples to an ion beam, you can look at the depth profile of the hydrogen. And there you see basically no hydrogen in the sample beyond the absolute surface layer. There's no signal in the deeper depths. And also when you look at XPS, there's, and then heat up the sample, look at the sulfur line, at the molybdenum lines, oxygen line here for comparison, and there's not much happening basically. So no chemistry happening. The water is only physisorbed on the surface. And when we look at the neutron scattering, what we did there is we went to a time of flight spectrometer, and we looked at the broadening of this elastic line. That's what's called quasi-elastic neutron scattering, and that tells you something about the diffusion, meaning that when the particles, in our case the hydrogen atoms or the water, move in the sample, then the elastic line will be broadened, and you will see a slight foot here that's typically following a Lorentzian broadening. And we saw such a broadening, so we saw some motion. And the analysis showed that this pretty much can be modeled by the diffusion of liquid water. So it's just the physics of water in cracks that we see. In the hydrogen beam bombarded molybdenum sulfide, we saw a very nice penetration into this sample in nuclear reaction analysis. So here we see in deeper depth a substantial signal, and we saw some signal on the first day, but then even much stronger signal a few days later after aging. So there is quite substantial uptake of hydrogen on these samples, and some slow diffusion process into this layered crystal after days. We also saw, when we looked at XPS, heating up the sample, that there is reactivity. There's not much happening on the molybdenum line, but the hydrogen seems to be strongly bound to the sulfur, and there's chemistry happening there. Now with the quasi-elastic signal, we see a bigger broadening than what we saw for the water-soaked samples. And here we see, interpret what we see as a diffusion of hydrogen ions. And we can also follow how with temperature, how this hydrogen desorbs. Basically a total desorption of the mobile hydrogen by 500 Kelvin. Now for the electrochemically loaded samples, where we really did model the process that you have when you do the electrolysis, there we saw even much bigger uptake of hydrogen into the sample. We saw much stronger changes in the XPS, in the X-ray spectroscopy, not only on the sulfur line this time, but also on the molybdenum line. So it's very strongly anchored. There's a lot of real reactivity happening there. And what we also saw is when we looked at the data with quasi-elastic neutron scattering, and these measurements were done in Munich at MLZ, there we saw actually two different lines in the quasi-elastic signal, means that we saw at the same time different processes of diffusion. And as one of the processes quite close to the speed with which we saw the diffusion in the atomic beam bombarded sample, we believe that we see really H2 motion, and we see hydrogen atom or hydrogen ion motion as well at the same time. So the conclusion of this, and it's nice to have all these different samples and have all the different techniques. And I think that's also the richness of the overall remade projects, that you bring these different analytical techniques together, because that provides the essential tool for understanding very complex systems like these systems. And what we found is that the liquid water actually, as you would expect, normally does not do real chemistry there, but you can access defective regions of the samples, so you have quite strong water uptake, but it doesn't go subsurface. In atom beam loaded samples, the proportion of mobile atoms increases with temperature, but you can also get complete desorption afterwards. That's not the case for the electrolysis loaded samples. They still keep quite a bit of hydrogen inside, trapped, and you see different diffusion processes there. Now I want to, after closing this, just show very briefly two other examples. One would be hydrogen diffusion in carbon materials, and that's a typical example of hydrogen storage materials that can be produced quite ecologically from existing carbons. And there we looked with a group from South America on a newly produced nitrogen-doped porous carbon. And in this study, we looked in particular on hydrogen motion as a function of temperature compared to normal exfoliated graphite carbon. And you see that the mobility is very, very strongly rich for this one, making very interesting storage material. You also have a very high hydrogen content for them. They can take up a lot of hydrogen. And you see this here compared in this plot of diffusion constant versus inverse temperature. Now, a different study that's very recent from colleagues from UCL in London, Fabrizia Foglia, and also CA has been at Grenoble has been involved in this. This is a study of the motion of hydrogen in all its forms, in the form of ions, in the form of water, in the form of being part of the polymer in fuel cells. They looked at how these different parts of the hydrogen move in this example, anion exchange membrane fuel cells. And the interesting part of this is that you can really look at the polymers themselves, or at the try to look at specifically built fuel cells for the neutron experiments. And by combining the different spectrometers, you can get a huge range of dynamics, easily 9 orders of magnitude apart. And by separating them out, by changing the temperature and by changing the relative humidity, you can really distinguish the different motions and get a lot of experimental information that's otherwise only available via calculations, molecular dynamics or DFT. A final science example would be also in the energy field, example of spin echo measurements that we did on non-fullerene organic solar cells. So there you can go through different points in the constituents diagrams of the different of the polymer blends, mixing different polymers, and look at the dynamics really as a function of momentum transfer, as a function of temperature, and trace how these mixtures changed your overall dynamics very much in detail. And also that's a very rich point where you can, with techniques like the Newton spin echo, you can look at the function of the dynamics as a function of time. Whereas with time-of-flight spectroscopy, you can look at the dynamics as a function of energy exchange, which are properties that are related to each other via Fourier transform. So you can get very global picture with these, combining these. Now I want to thank and list a lot of collaborators. I certainly have forgotten one or two. I apologize for that. And for the funding that we receive for all this research, and I thank you for your time, and I'm open for questions. Thank you.